And Aditya has kindly shared slides with myself, so I'll put that in the chat as well. And Aditya, feel free to go away.
Thanks very much, Grace, for having me, and everybody else for organizing this beautiful graduate sort of symposium. I'm going to share my screen, and I'm going to go full screen now. Great. I'm going to discuss an application of topology to pendulum systems. And is there a way in which you could explain the number of compositions in pendulum systems using topological arguments, which usually do not seem relevant to a complex system like a pendulum system because it could be very chaotic and you could have a number of background conditions. But in this case, you will see that it's quite useful. But the answer to this question, and I'm going to put a spoiler here, would be no. Even though topology is a great way to explain this particular physical event, it's not really sufficient. But then what comes out of the whole inquiry and the whole process of discovery is quite interesting. Let me discuss what I mean by causal explanation and then what I mean by a non-causal topological explanation. So let's say you are asking a question, you want to explain a particular event D, and the usually you do it is that you say, okay, A leads to B and C to D, right? ABC could be physical laws, it could be physical events, could be variables, and so on. If you change the variables, if you change the causal history of the event D, you might get a different event, right? You might get D1. But when you explain things non-causally, that is, you are not latching yourself to the causal history of the event, you're trying to figure out a way in which things wouldn't have been different, even if the causal history would have looked different. For example, if the physical laws were to change, let's say, if this was A1, B1, C1, the sequence of events, A2, B2, C2, or A3, B3, C3, it would still give you the effect of the outcome as D. So D wouldn't change irrespective of a change in physical laws or physical events. And what really constrains the behavior of D or the outcome of D is some sort of mathematical framework, in which case this is topology. So I'm going to explain how topology is useful to constrain physical systems despite a change in the physical laws of the particular system. Just very briefly, why a growing interest in non-causal explanations? Because usually you explain complex systems, and you have to go a long way to explain what happened in the complex system. But when you talk about a non-causal explanation, it's just a topological explanation, you can bypass a lot of things in the system, and you could have a very simple explanation for something that could be very, very complicated to explain. I could run into pages and pages. We'll see that. So it clearly shows that in complex systems, some causal laws are not really critical to the explanation. And even if we didn't know them, or even if they were to change, the outcome would remain the same. But what's an important question is that, well, how is that even possible, right? I mean, if a feature of a complex system remains invariant, it is the question, well, how are such non-causal explanations even applicable to such complex systems? But I mean, I'm going to call them as DMEs, or distinctive mathematical explanations, because they essentially invoke just mathematical necessities. Here's the plan of the talk. I'm going to introduce the causal explanation first, then we'll head on to non-causal explanation for double pendulums, and I'm going to extend that to any n-tuple pendulum system, which can contain n number of members. I'm going to use very basic results in topology using Morse inequalities, Euler characteristic embedding numbers. But then I'm going to show how the explanation is really inadequate to explain what we're going to explain, and potential ways out of it, including catastrophe theory, which is a very interesting development in studying critical differential functions, and how it fails in terms of this particular physical explanation. And then we can do the presentation. Okay, let's begin. So what you see in front of you is a pendulum system. It's a double pendulum. So you have two rods suspended from a pivot. So a rod of length L and a rod of length K. The angles of inclination are alpha and beta. And the heights of each of the bobs are Ym and capital Ym, pretty basic physics. And as the pendulum system moves, as you can see in front of me, so if I move this, the pendulum comes to equilibrium when the net force on this system is 0. So on a double pendulum, the net force is 0 at in 4 positions. So one position is where both bobs are right down. The second would be when one bob is right down, one is right up, and the third is just the opposite. Third and fourth, just the opposite. So if you count them for a double pendulum, you have 4 equilibrium positions. Now, one way to talk about this is to find out the net force in the system at each of these points, which is quite cumbersome. Or you could just talk about the P function of the pendulum system, which is the potential energy function, which essentially just invokes the height of the bob. So if you find out how the bob varies with the angle of inclination, and if you write the PE function, which is mass times acceleration to gravity and the height of the bob, the first bob and the second bob, you add them up, and then you take a partial differential, which tells you well how each of the bob varies in its potential energy as it moves along its trajectory. So once you differentiate that, very simple maths and very simple physics, you find out that there are 4 equilibrium positions, right? At the angle 0, 0, which you see over here, 0, pi. So this bob is at angle of 0 degrees, this is at pi degrees, pi, 0, and pi. And because the bob can traverse, one complete rotation and then can come back to the same position, even if it's the same physical position, it's a different geometrical position, right? You just add 2 pi to that. So for any double pendulum, it's almost a fact that there are 4 or more equilibrium positions. Now, what's a non-causal way of explaining the same event without invoking the PE function? So one explanation could be that there are 4 or more such positions because the PE function of the pendulum system can be mapped to its configuration space. I'll discuss what is a configuration space shortly. And because the configuration space has a certain number of critical points, hence the pendulum system also has a certain number of critical points. A different version, which I'll explain. So D1 was given by Mark Lange, who is a distinguished professor at North Carolina. D1 is my version, and D2 is my version as well, which is an extension of this explanation. So the number of positions of an pendulum system is at least 2 to the power n, because the P function can be mapped to its configuration space and gives you an n torus, which has certain topological invariances. And D2, which is to say that so and so number of positions for a double pendulum or any double pendulum, because and this is a different way to explain the same phenomenon, but that the lower bound on the number of equilibria of the pendulum system with k stable direction, where each stable direction is just around one down. So this is stable. This is a stable equilibrium. What do you see right on the side of me? Not sure if it's visible. So this is stable, and when the rod is up, it's unstable because when you push the pendulum to the side, it will not come back to the same position. So the number of k stable directions is equal to the kth Betti number of its distorted configuration space, which is an n torus. Let's get started. I'll explain this one by one and then show why this is inadequate. So what's a configuration space? It's essentially a manifold which represents all physical points or all possible points that a physical system may realize given its geometrical constraints. So for a simple pendulum, if you have just one bob in front of you, it can traverse a circle, so its configuration space is a circle. For double pendulum and higher pendulums, things get slightly different because you take a product space and you don't just draw concentric circles. So for double pendulum, the configuration space is a torus because each of the rods can traverse a circle. And you take the product space of circles, so S1, cross S1, and you get a torus. And for n double pendulums, it's an n torus because you can take the product space multiple times, n times. It's because it's manifold, quite straightforward. It has a genus. This manifold has a genus which doesn't change when you bend and twist the shape, and it has other invariants such as your characteristics, which is chi, and number of critical points as well. So it's a basic result in topology that for any smooth, compact, and rotatable surface, chi is equals to n max minus n saddle plus n min equals to 2 minus 2g, where g is the genus, and n max is the number of maximum critical points, n saddle is the number of saddle points, and n min is the number of minimum critical points. So let's take an example. Let's talk about a torus. The torus has genus 1, so chi is 0. So the number of critical points of its configuration space follows this invariance, follows this equality, which is n max minus n saddle plus n min equals to 0. Let's see why this is useful. So when you study differentiable functions to find over a manifold, you sort of establish a mapping relation between a manifold and the space of real numbers, where you can define a function, which is over here. And what you can do is that you can take the physical system and you can map its potential energy function, which is a differentiable function. And this is a basic physical fact because if a P function is not differentiable, it can't be a P function. It comes from Newton's laws. So because the P function is a finite and continuous, it can be defined, it can be mapped to the configuration space. And you could think about distorting the configuration space by mapping the P of each of the points that the pendulum system sort of traverses. So you multiply the P of each point to the configuration space and you define a height function over the configuration space. Once you define that, you'll get a manifold, you get a nice manifold, not so nice manifold because it's a distorted version of the same torus. But what's interesting is that this manifold will also have the same invariance because the transformation is homoeomorphic. It doesn't really change topological invariance. So n max minus n saddle plus n min equals to 2 minus 2g is also going to be true for a distorted manifold where you have mapped the P function on the configuration space, which is also a distorted torus. For torus, G is 1, so this is 0. And for a surface, it's a basic result from compactness that it's at least one maximum, one minima, so 2 critical points. And because you must satisfy this equality, so 1 and 1 over here, and this must be 2, this should be 0. So there are 4 critical points. Now, what's interesting about this explanation is that we didn't really have to invoke what the pendulum is made of, if it's a spring pendulum, if it's a stiff pendulum, if it's a non-stiff rod-based pendulum, if it's a compound pendulum, it doesn't really matter, right? For any level pendulum, the configuration space is going to be a torus. And the configuration space, when it's mapped to its P function, it's going to be a distorted torus, and you can bypass all the complicated mechanics of the system, and you can just use this very simple looking explanation to find out what is the constraint on the number of equilibrium positions of this pendulum system. So Lange in his book, Because Without Cause, published quite recently, argues that this is a non-causal explanation, but it's a DME, essentially, because it reveals why all such pendulums have 4 or more such equilibrium positions. If you were to explain why a compound pendulum has such and such number of positions, you have to go through the causal history, right? But in this case, you could just explain this as a unifying explanation for all kinds of pendulum systems. Let's skip this point. This could get a bit more complicated. But then I'm going to extend this explanation to cover any n-tuple pendulum systems, and this just uses basic Morse theory. So Morse theory tries to understand how a manifold shape constrains the distribution of critical points, which are defined over it. So this is not a Morse function. This is a basic open shape. So A is a minima, C is a maxima. A has the index 0 because there's no direction that you can travel from. From A, C has an index of 1 because there's one dimension which can travel downward from C. B's index is undefined. This result is important for us because it's an inflection point. It's a degenerate point. And a degenerate point is important because when you map differentiable functions onto configuration spaces, it could be possible that several non-degenerate points could be crumbled into one degenerate point. So B1 and B2 could be crumbled just into B. So degeneracy in a differentiable function affects the number of critical points when you define it over the configuration space. We're going to use this result to understand how we can extend this. In higher dimensions, we talk about n-tuple pendulums for which the configuration space is n torus and not just a 3-dimensional torus. The next is defined using the Hessian of the function. So Hessian is defined as, for a function from M to R, the Hessian of a function f, which is a P function in our case, the potential energy function, at a point f is defined as it's a double partial derivative of the P function. And the number of negative eigenvalues gives you the index of the critical point. So in n dimensions, if you want to find out how many downward directions are available from a critical point, you just need to find out the Hessian and find the number of negative eigenvalues from that critical point, for that critical point. If a point is non-degenerate, which it's a normal point to deal with, then the Hessian will be, the D of the Hessian will be non-zero. Whereas for degenerate points, the D is going to be 0 because any of these diagonal entries could be 0. But what's also important here is that when you calculate the index of a critical point, the index calculation invokes causal processes because you have to trace the causal history, write the P function, take the Hessian, find eigenvalues. So, it's a long process and it has to be done on a case-to-case basis. Let's just keep that in mind, and that'll be useful afterwards. What are Morse functions? So Morse function is any function defined from, a surface or a manifold to real numbers, real numbers. If every critical point of the function, critical point P of the function f satisfies 2 criteria. One, that P is an isolated critical point, and P is a non-degenerate point, which is that its point is not an inflection point in analogous to a surface. And for every Morse function, this is a fundamental and very important result of Morse theory, which connects the number of critical points to its topological invariant. Is that the Euler characteristic of the manifold is equal to the index of the critical point, minus 1 power k times n power k. So the number of critical points having a particular index k, when you sort of add them up, that's going to be equal to Euler characteristic. That's the basic result of Morse theory and quite important result for dynamical systems and complex systems. But if P is a non-degenerate point, then there's no problem because the Hessian comes out to be non-zero. How does it look in terms of functions, P functions? So let's take a very basic example. If a function is x squared, that's a P function. This is a Morse function because at the critical point x equals to 0, f double dash and f dash, are f dash is 0, but f dash double dash is non-zero. So this is a Morse function. But x cube is not a Morse function because at the critical point x equals to 0, f double dash is equals to 0, which means it's a degenerate point. Important result for us. We'll use that to establish why the explanation is inadequate shortly. Just to demonstrate, so if you want to explain the number of positions of an n-tuple pendulum system, you could just fit in index and index the number of critical points having a particular index. So let's say you're talking about a simple pendulum, plug in, it's a circle, that there's a minima, there's a maxima. Minima has index 0, so you plug it over here. There's only one minima, so 1 into -1 plus -1 times maxima, there's only one maxima, which has index 1. So you just fit in the data here, and you'll see that for every pendulum system, this equality is going to be satisfied. And same for spherical pendulums, or any pendulum system, essentially. I'm going to skip the demonstration in the interest of time. So for any n torus, which has g equals to 1, that's the topological invariance. For any n-tuple pendulum systems, this is the constraint that every pendulum system must follow, which is -1 power k. K is the index of the differential function, and k is the number of critical points equals to 0. So it constrains the distribution of critical points over the n torus, which is the PE function when defined on the configuration space of the system. There's a concern, though. I mean, if you have just an n torus, you could find out what are the number of critical points of the n torus. But when the n torus is distorted because you've defined the P function on the n torus, the torus can be distorted in a way that you don't really know what are the number of critical points and what are their indices. That's a problem. So because that is the case, you must then use the Hessian to find out what is the index in each of these cases. But that defeats the very purpose of using a non-causal explanation, because you don't really know what's the index. So is there a better way to explain this system? I'm going to skip a lot of text and just going to come to the point here. Is there a way in which you can avoid using the Hessian, but still use topology and yet explain the number of such positions, successfully? I suggest that there's a case. So you can use Betti numbers to do so. This is D2. We've just discussed D1. D2 uses Betti numbers, and Betti numbers are essentially topological invariants for most functions that are defined over manifolds. So let's say if it's a circle, B naught defines number of connected surfaces. B1 is the number of holes in one dimension, put it very simply. B2 number of holes in two dimensions. So for a circle, there's one connected surface, so B naught is 1. B1 is 1 because there's just one hole, which is one dimensional. No two-dimensional holes, so B2 is 0, and so forth. Same for a torus. B naught is 1, there's one connected surface. B1 is 2 because there are two one-dimensional holes. B2 is 1 because there is only one two-dimensional hole, and then there are no three-dimensional holes. So this is 0. The kth Betti number shows the number of k-dimensional holes. This is an important result because it connects the number of critical points of the P function defined on the configuration space. So D2 suggested that there are 4 or more such positions for any n-tuple pendulum. This should be 2 to the power n, sorry about that, because the lower bound on its number of equilibria with k-stable directions is equal to the kth Betti number. So k-stable directions essentially implies, so if you look at this pendulum system over here, so this is 1, 2 stable directions because they're both stable. They're both pointing downwards. This is one stable direction. This is unstable. Here, both are unstable. Here, there's one unstable direction, which is upwards, and the second bob is stable because it's pointing downwards. So there are 2 positions where you have, sorry, there's one position where there are 2 stable directions. There is one position where there are 0 stable directions, right? There are 2 positions where there's only one stable direction. And you could trace this result without going to the P function at all. You could just use Betti numbers. So let me demonstrate this. As I've just mentioned, for a torus, this is the Betti number. So let's say you have 2 stable directions. So you find the Betti number using NCK, which is 2, 1, two stable directions, when only one node is pointing downwards, and that equals B1 equals 2. That's a very interesting result. Or 2, 2, and so again NCK, which is one stable direction when both rods are pointing downwards, which is equal to 2 beta equals to 1, and 2, 0, which is one stable direction, which is just beta equals to 1. So the k Betti number is equal to the number of k stable directions. Also, interestingly, when you add up all the Betti numbers, at least in this case, when you use Pascal's binomial identity, you find that when you sum it up, you get 2 to the power n as the total number of equilibrium positions of this pendulum system. This result was not available using just the Euler characteristic because we didn't really know, because the index was not defined. We didn't know that for a distorted n torus, what is the index and what is the total number of critical points. But in this case, you're pretty sure that you at least have a lower bound on not just the number of stable directions of a pendulum system, but also the total number of equilibrium positions that is constrained by the Betti numbers, because it controls how the critical points of the function are distributed over the manifold. But then what's the concern with these explanations? And one of the major concerns is that when we talk about these functions, we always assume that there are most functions. But a lot of interesting things come out when you investigate systems that have the P function, which is a non-Morse function. So, and the explanation breaks down. But the discovery is interesting, and I'm just going to discuss that briefly. So I'll explain when this is inapplicable. And this is inapplicable when you introduce perturbations in the physical system. And you could introduce perturbations in two different ways in which explanation fails. So one way could be that you take a critical point that become degenerate because the P function is just varying in a very strange way, which makes it sort of difficult, and in some cases impossible to calculate the index of degenerate critical points because it's not defined in a number of cases. Or you could find a P function that is no longer mappable to a manifold, right? Because the P function or a closed and a bounded manifold, because the P function is just too wild. And hence you can't apply Morse inequalities to this particular physical system. So I'll discuss both of these cases and then discuss what's a potential way out, and then suggest that this is not really a potential way out because it also fails in some cases. So let me perturb the length of the rod L. So the pendulum system that we had in front of us, I'm going to change the length of the rod dynamically. And then I'm going to put some restrictions here in case A. And I'm going to relax the restrictions later on. So let's say you impose certain constraints on the internal perturbation. So the rod could dilate or could contract in length depending on internal external parameters. So I'm going to add a G alpha function here for a simple pendulum. This is the potential function of a simple pendulum. So length times cos alpha. I'm going to add a simple perturbation G alpha with two constraints. The first constraint is going to be the P function must be continuous, because if that is not continuous, it will violate Newton's second law. So I'm going to put this constraint. So it must be defined over a circle. So U alpha part alpha is equals to part alpha minus 2 pi. So the same P at the same points in a circle when you sort of traverse in two different directions. I'm going to put another constraint, which is U dash part alpha. So its first differential is also continuous because the differential of P function defines the force at that critical point. And the force at a critical point cannot be two different forces because that will again violate Newton's second law. You just can't have that. That's also a constraint. And third constraint is that the double differential is also going to be continuous. So defined with the circle, same circle for a simple pendulum. And then I'm going to show how you can extend this case to more complex pendulum systems shortly. So let me take a very simple perturbation, which is perturbation which looks like sine alpha. And I'm assuming that the length of the pendulum system is just 1, so 1 unit. So 1 cos alpha, and I've just added sine alpha as a perturbation. So when you study the P function in this nice space, what you find out is that so this blue dot is the P function. The black one is the P function differential, which defines the force, which means when the P function becomes 0, or this critical point, it means that it's a stable position for the pendulum system. It's a critical point of the pendulum system, not a stable position really, not in all the cases. The red dash is one where you have, we're trying to find out if the function is non-degenerate or not. So if you look at this particular diagram, you'll find that at minus pi by 2, at minus pi by 2, and other positions, this function becomes degenerate. That is not just that U dash is 0, but U double dash is also 0. So U double prime is also 0. So the function is degenerate, which means that you can't really find the index unless you do certain things with the function, which I'm going to discuss shortly. Take another perturbation, which is sine square alpha. I'm going to use a different length of the pendulum system. So U part alpha looks like 2 plus sine square alpha times cos alpha. And with this perturbation, what's interesting is that every critical point is going to be degenerate, which means that you have no clue what is the index of these critical points. So you can't even use the explanation, right? Minus pi, minus 2 pi, pi 2 pi, and so forth. So every n pi is going to be a degenerate point. And in fact, in this particular case, the degenerate point is quite badly degenerate, right? And why is that the case? Because if you look at the second derivative of the P function, second partial derivative of the P function, this is also flat, right? Because it's flat, the third derivative is also going to be just 0, and so forth. Even the fourth one is probably 0 as well. So I mean, so therefore for these perturbations, and you could take a number of other perturbations, you can't really find the index of critical points. You can't. It's not a Morse function, so you can't use the explanation. But then there's more to the story. We'll come to that shortly. Also, when you distort a torus, you could distort it in a way that has only it has only 3 critical points and not really 4 critical points. So Kritseva showed that you could have mappings between functions that are continuous immersions of, let's say, certain kinds of function over these manifolds, which are continuous and which would give you degenerate tori, which have just 3 critical points. So the result that follows from Morse inequalities that there are 4 or more critical points for a torus is not really true for such immersions. But again, the concern is that whether such immersions are, legitimate P functions is a cause of concern. I'm not sure if they are. I have to establish them more formally. But if they are, then it suggests that not every double pendulum is going to have four equilibrium positions, because the P function might behave in a very strange way where you have just 3 critical points and not really 4 critical points. Let's talk about a different case. So we spoke about case A, where you had perturbations that still sort of followed a continuous mapping. In case B, if you relax restrictions concerning case A, you have mappings that are not smooth, right? They're not compact. And the strategy of studying such functions on manifolds fail. So take different perturbations. So perturbation is alpha square, where alpha is the angle of inclination of the pendulum system, pendulum rod, and take another perturbation, which is probably a nicer perturbation. So in both of these cases, the pendulum system is going to fly out of its path space, and it's going to become bigger and bigger with time. So in that case, the configuration space is still a nice torus, but the P function is just a wild and open, wild and open geometrical shape, and you can't really map that, and that's visible when you trace the P function. You see that if you look at minus pi to pi, so minus 3.14 minus 3 plus 3.14, you see there is only one critical point for simple pendulum. That's interesting because you would expect that for any simple pendulum, like the one that's in front of me, there should be at least 2 critical points. But that's not the case, right? When the pendulum rod is contracting or dilating at a very high rate, the P function may just give you 1 critical point for the pendulum system, which means for n double pendulums, it's just n critical points and not really 2 to the power n critical points. And this function is also degenerate at alpha equals to 0, which makes the case a bit more difficult. And you could take perturbations of alpha cube, doesn't really matter. You could take alpha cube plus alpha square. So the point is that there's so many functions that have, I'm going to skip this demonstration, or you could take a quadratic function, perturbation, which also gives the same result, that it becomes degenerate in these conditions. So you have a large number of functions, even though most functions are Morse functions, which are not definable over a manifold, and which have a number of degenerate points in the P function. You could extend this result from simple pendulums to any n double pendulums, and it's quite straightforward. So you write the Hessian first. I'm going to write the Hessian here. So let's say for a simple pendulum, for a double pendulum. So these guys are going to be 0 over here. So dou to u by dou a dou b, and dou to u by dou b dou a, because the P function has only 2 variables, alpha and beta. So you differentiate them twice, take alpha and beta. So these take the values as 0. Which means that the D of the Hessian is just going to be just that. So dou to u by dou alpha square. And for the D to be 0, each of them must be 0, which is the same condition as a simple pendulum. So no different. So if you have any n double pendulum system where, so this is, let me just get back to here. So for any n double pendulum system, if you have perturbations that are independent, which means that the n variables and they're not sort of compounded together, you will get a condition where the degeneracy condition for any n double pendulum will be exactly the same as for a simple pendulum, right? No difference. So a perturbation that makes a simple pendulum P function a non-Morse function will also make the P function of any n double pendulum system as a non-Morse function. And hence you can extend the same argument to any n double pendulum system. I'm going to skip this demonstration. Not really important for our purposes. Great, yeah. So the point is that for any n double pendulum system, the explanation generally fails because not all pendulum systems have the same number of equilibrium positions, and even if they have them, you can't explain them using topology. There's another interesting case where you have configuration spaces that are non-smooth, right, or which behave in very strange ways. For example, if you take a spherical pendulum, which is pendulum suspended over here, so it can move around the horizontal axis, and then you have a frame which could sort of move 360 degrees around its pivot. And the resulting space should be a spherical pendulum. And when you map out the configuration space of the system, it turns out to be a non-smooth tori, right? Or it bifurcates in a way that you actually get 2 tori instead of getting a sphere, which is the typical configuration space for a spherical pendulum. So Richter et al., they note that when you implement, a spherical pendulum in theory has a spherical configuration space. But in practice, there is no spherical pendulum that has such a configuration space. That's very strange result. So no matter how you design a spherical pendulum, no matter how you physically implement the system, how you chose to present the mass on the sphere, it is impossible to do so, and it will always change the configuration space of the pendulum system. It will be different from S2 in probably all the cases, as you can see here. So in this case, this bifurcates into 2 different tori, and it is not really a sphere, which means that for this pendulum system, again, you cannot use the P function. You can't map the P function because the Morse inequalities are not applicable for this particular case. Details are not relevant. I'm going to skip that for now. But then other ways in which you can sort of bypass the problems that exist with degenerate points. So there are several results that do that prove degenerate Morse inequalities in certain cases. So Bartsch will prove this for Hilbert manifolds, which is n-dimensional manifold, with the assumption that it's a 2 pi periodic manifold. But then the problem is that, and I'm going to discuss this very briefly here because of that quite a lot of time, that not all P functions are periodic. So you just saw a case before where we had alpha square perturbation, and the perturbation only had just one critical point within a 2 pi period. And the period was changing every time the pendulum rod would increase in length or would contract in length. So this result is again not applicable because it is not necessary that the P function is going to be periodic. Popescu, his thesis at MIT 2004, showed that you could use heat flow vectors defined over a manifold and study the number of critical points for which are degenerate. But then this result includes non-compact manifolds, so it's not really true for compact manifolds. So I'm gonna skip that as well. And Bismuth, improvising on Witten's account, he shows this for Morse-Bode functions. Morse-Bode functions, are a more general case of Morse functions where, a critical point should be only non-degenerate in a direction which is normal to the tangent space of the manifold at the critical point, but not in every direction, or not in every direction. The problem is that, Morse-Bode functions, not all P functions are Morse-Bode functions, because it could be true that in the case of sine square perturbation that we saw earlier, the point was degenerate in every single direction. So it's not even a Morse-Bode function. So you can't even use this account to sort of bypass the problems with degenerate degenerate critical points. So again, an interesting result was given by René Thom, a French mathematician, and in a recent book by Castigliano et al., which is the revised version, they sort of combined this result using catastrophe theory, which brings in all the relevant classification schemes for degenerate critical points, and it extends more to deal with these nasty points. So there were two theorems given by René Thom, a French mathematician, that deals with this problem, and they focus on a change in the number of critical points of a degenerate point when it's perturbed. So take a simple example. So let's say you have a function that is x cubed, and you put a nice perturbation, a simple perturbation, which is ux. So when u is more than 0, there's only one critical point, which is over here, the origin. When u is equals to 0, the point is degenerate, it just becomes an inflection point. When u is less than 0, the point bifurcates into 3 critical points, right? An interesting result. Depending on the perturbation that you introduce in the pendulum system or in the P function, the number of critical points might change, quite radically. And as the number of variables change, number of parameters change, this is going to change quite substantially as well. So what René Thom did in catastrophe theory, or at least in solution theory, was that he gave a classification scheme. He said, well, no matter what the function is, you could classify them, very strange functions, into these 7 basic categories. So you could classify them as x cubed, x4 unfolding, x5, x6, x3 plus y3, x cubed minus xy squared, or x2y plus y4. So if you use Taylor's expansion, you could sort of mold the function in a way that you can represent it as one of these 7 elementary catastrophes. And once you have classified a particular function into these elementary catastrophes, then you know how these functions behave when you introduce perturbations in these functions. So even if the point is going to be degenerate concerning these functions or concerning very strange functions, which could be classifiable into these categories, these basic 7 categories, you already know beforehand how the critical points of how a degenerate critical point is going to behave when it's bifurcated, right? So you could study even very complicated functions using this classification. And the second theorem of Thom is that this classification remains stable under small perturbations, not under large perturbations, because when you disturb the function, you would see that if u is small enough, the same classification scheme is valid for the function. The problem is that the classification scheme can only take max 4 variables, in some cases 5 variables. So if you have a nasty pendulum with a lot of variables, which includes perturbations, external factors, wind and things like that, this classification scheme is not going to be sufficient for its purposes. When perturbations are interdependent, for example, if my second rod is going to depend, the perturbation of my second rod is going to depend on the first rod, in that case, the number of parameters are going to increase further. And because they increase beyond 4 and 5, you can't really use catastrophe theory. So you can't classify them as being in a particular elementary catastrophe. Plus, you need to manually classify points, right? If before writing the P function, you would not even know what classification scheme does this potentially degenerate point in the P function falls under. So it's not obvious by just glancing at the function. So you can't really use a non-causal explanation because you don't really know what's happening with the P function, because the Hessian is available only when you examine the P function and not beforehand. For example, it's not obvious that the function, h sine beta into alpha minus sine alpha, which are two angles of inclination, is an X3 catastrophe, right? It's just not obvious. You have to take a number of steps in establishing this fundamental result. So you can't really know what a P function looks like at a degenerate critical point into these elementary catastrophes. And we've just discussed that. There's always the worry that some P function will escape this classification. And plus, this is not really valid for large perturbations, right? I mean, you could use perturbations in pendulum systems that just are not classified under the scheme. And also, you have to use the Hessian manually, which again goes against the very idea of non-causal explanations, where you're bypassing all the complex mechanics of the particular system. So let me just summarize this talk and what we've discussed so far. So we've discussed 3 explanations for pendulum systems. One was, I've discussed 2 explanations. One was a causal explanation, which included just the P function, where we spoke about when you differentiate the P function, how does the critical point of the P function varies and how it gives you the number of critical points of the pendulum system. Then we discussed non-causal versions of the explanation. We discussed D1, D2, and its extension. D1 was a version that was given by Mark Lange, which applied to only double pendulums, which use Euler characteristic. Then we used D2, which extended D1's extension, which extended this to any n-tuple pendulum systems, which had the complication spaces and torus. Then we spoke about D2, which included Betti numbers and how Betti numbers constrain the distribution of critical points and stable critical points within the pendulum system. But then we saw modality essentially means when the explanation was successful or not. So the explanation was modal, or it was necessary, or it would give a correct result only in case of Morse functions. For non-Morse functions, that failed because of 2 reasons. One, because of introduction of degeneracy in certain strange P functions, and second, because the P function may not be mappable to a smooth and compact configuration space. And we just discussed that shortly. We discussed the ways out. We discussed catastrophe theory briefly, and other results that extend Morse inequalities to degenerate cases. We saw that it was not adequate to cover more complicated cases. So my verdict was that these explanations are useful. They're quite quite nice explanations, simple explanations of these systems, but they're not general universal explanations or non-causal explanations of the physical event as to why we obtain such and such number of equilibrium positions of any double pendulum system or for a double pendulum system. Because either index calculation was causal, as you can see here, we had to use a Hessian, or when you introduce perturbations, the system just failed to be accommodated within the P functions. Sorry about that. Within the framework of topology using invariance. So we have to do all the hard work in establishing and understanding the critical points of such complex systems, and a topological shortcut, even though it's quite handy in some cases, doesn't serve very well in more nuanced cases. Now, you might ask the question, well, can we extend this result to more systems, more oscillating systems? You could, and this is work in progress. So I'm looking at systems that have Hamiltonians, which is when you add the P function and the kinetic energy function, which are integrable, which means that integral systems follow a certain invariance, topological invariance, and you could study them nicely using topology. And there's a certain theorem, which says that under small perturbations, the topological invariance remains stable for any integrable Hamiltonian system. This is under research, and I'll discuss that when I have more details with me. But for me, that's all for this talk, and these are the references for the talk, and I'll be happy to take any questions and look forward to your comments as well. Thank you very much. Stop sharing my screen.
Thanks, Aditya. Do we have any questions for the speaker? I had a question, but you kind of answered it at the end. I was going to ask about if there are any other physical systems that you can extend this to, but it seems like this is your work in progress at the moment. Do you think when you look at maybe more complicated systems, more kind of areas of topology or topological invariance could come in or come in handy when kind of looking at them or describing them?
Right. I mean, so my concern is that the results that we have that really connect complex systems to topology, one of them is Morse theory. I'm not aware of more results. If you have more results, I'd be quite happy to know about them. And because Morse theory is one of the fundamental results that connects differentiable functions to manifolds, this is pretty much what we have when we explain systems using topology. There's another nice explanation that uses, have you heard of the Borsuk-Ulam theorem? Probably a lot of you might have heard of the theorem. The theorem says that, so if you have a sphere, so let's take a nice sphere, and if you have a continuous mapping on the sphere, so let's say I'm defining a function that is a height function, let's say over a nice circle, the value of the height function is going to be the same, at least on two antipodal points, right? So let's say you use a continuous function that is temperature function or a pressure function, and you ask the question that on this Earth, which is sort of a sphere, are there two antipodal points, which are opposite points on Earth, where the temperature and the pressure are exactly the same? So Borsuk-Ulam theorem answers this question and says that, well, on Earth, there are going to be at least two antipodal points where the temperature and pressure are going to be the same, irrespective of what happens on the weather. It's crazy. I mean, physical laws might change completely, but the theorem says that it's going to be the same. I'm sort of working against explanation. My hunch is that this is not really true, because temperature is not a continuous function, and you could trace this out using statistical mechanics and say that, well, this is true in most cases, but it's not as straightforward as that. So you could use Borsuk-Ulam theorem, or you could use other theorem like intermediate value theorem, or anything that connects functions, nice functions to topological manifolds could be handy in talking about these things. But then I suppose that it has to be done on a case-to-case basis, and we don't really have, at least in philosophy, we don't really have a theory that connects non-causal explanations in sciences very generally to a general mathematical framework. So the different explanations and the different frameworks to explain the explanation. I mean, what I'm trying to say is that there are different theorems that explain different events, and there's not one theorem that sort of binds all complex systems in one nice broad category. So probably there's a lot more work to be done, and I suppose that's all I have to say about this particular question. That's a great question. Thank you.
Very cool. Thank you. Are there any other questions for the speaker?
Yeah, I had a quick question. Good talk. I just wondered, so I'm not an expert in Morse theory, but is there somehow like a way you could look at higher order derivatives of the critical point to somehow connect that to the topology? Because every time I see Morse theory, it's about the Hessian, right? But could you go to the third derivatives and think about that somehow?
I'm not really sure. I'm not expert in Morse theory either. So I'm trying to say that when you find the third and fourth order derivative, you might be able to define the index of a critical point because you're looking at a higher order derivative. That could be an interesting way to look at this theory. And has it been done before? I'm not sure if I've seen a result like this. I've searched quite a bit. Well, I mean, one of the ways in which you can look at these functions is to look at singularities in these critical points, and you look at singularities by studying its higher order derivative. So a critical point is different from another critical point which has the same degeneracy in the second order because its higher order derivative looks different. The classification scheme in part can come from characteristic theory, but I do not really know if you have a general framework that uses higher order derivatives to classify the index of a critical point using higher order derivatives. So not really sure if we can have sort of a general way to figure out the index using third or fourth order derivatives. I'll look into that. That's a good question. Thank you.
Interesting. Thank you.
Great, thanks. If there aren't any more questions, then maybe we can thank the speaker again. Thank you very much for your talk, Aditya.
Thanks so much.
So I'll stop the recording.